we have only discussed in this course electricity. Calm down. But this course is about electricity and magnetism. Today, I'm going to talk about magnetism. In the 5th century BC, the Greeks already knew that there are some rocks that attract bits of iron. And they are very plentiful in the district of Magnesia, and so that's where the name magnet and magnetism comes from. The rocks contain iron oxide, which we will call a magnetite. In 1100 AD, the Chinese used these needles of magnetite to make compasses, and in the 13th century it was discovered that magnetites have two places of maximum attraction, which we call poles. So if you take one piece of magnetite, it always has two poles. Let's call one pole A and the other B. A and A repel each other, B and B repel each other, but A and B attract each other. There is a huge difference between electricity and magnetism. With electricity you also have two polarities, but you are free to choose a plus or a minus pole. With magnetism you don't have that choice. The poles always come in pairs. Isolated magnetic poles do not exist, or as a physicist would say, magnetic monopoles do not exist as far as we know. If anyone finds a magnetic monopole and don't think that people are not looking, that would certainly be worth a Nobel Prize. In principle, they could exist, but as far as we know, they don't exist. They have never been seen. Electric monopoles do exist. If you have a plus charge, that's an electric monopole. You have a minus charge, electric charge, that is an electric monopole. If you have a plus and a minus of equal strength, that is an electric dipole. Whenever you have a magnet, you always have a magnetic dipole. There is no such thing as a magnetic monopole. In the 16th century, Gilbert discovered that the Earth is really a giant magnet, and he experimented with compasses, and he was effectively the first person to map out the magnetic field of the Earth. And if you take one of those magnetite needles, and the needle is pointing in this direction, which is the direction of northern Canada, then by convention we call this side of the needle north, and we call this side of the needle south. Since A repels A and B repels B, but A and B attract each other, in North Canada is the magnetic south pole of the Earth, not the magnetic north pole. That's a detail now, of course. So this is the way that we define the direction, north and south, of these magnetite needles. A crucial discovery was made in 1819 by the Danish physicist Ørsted. And he discovered that a magnetic needle responds to a current in a wire. And this linked magnetism with electricity. And this is arguably perhaps the most important experiment ever done. Ørsted concluded that the current in the wire produces a magnetic field, and that the magnetic needle moves in response to that magnetic field which is produced by the wire. And this magnificent discovery caused an explosion of activity in the 19th century, notably by Ampere, by Faraday, and by Henry, and it culminated into the brilliant work of the Scottish theoretician Maxwell. Maxwell composed a universal field theory which connects electricity with magnetism. And that is at the heart of this course. Maxwell's equations. You will see them all four, by the end of this course. If I have a current, a wire, let's say the wire is perpendicular to the blackboard, and the current goes into the blackboard, I put a cross in there. If the current comes out of the blackboard, I put a dot there. And there is a historical reason for that. You've always talked about vectors in 1801 and in other courses, but you've never seen a vector. And I'm going to show you a vector. This is a vector. And this is when it comes to you. That's when you see a dot. And this is when it goes away from you. That's when you see a cross. So this current, when it's going into the blackboard, I can put these magnetite needles in its vicinity, and they will then do this. And when I put it here, it will go like this. And they follow the tangents of a circle, and this is the way that we define magnetic field and the direction of the magnetic field, namely that the magnetic field, for which we always write the symbol B, magnetic field, is now in the clockwise direction. By convention, current goes into the blackboard. And if you ever forget that, use what we call the right-hand corkscrew rule. If you take a corkscrew and you turn it clockwise, the corkscrew goes in the board. That connects the B with the current. If you take a corkscrew and you rotate it counterclockwise, then the corkscrew would come to you, comes out of the cork. And that's how you find the magnetic field going around current wires. It's just a convention. I want to show you how a magnetic needle responds to a current. I have here a wire through which I'm going to run a fabulous amount of current, something like 300 amperes. And you're going to see that wire there. I'm going to get my lights right. Let me see how I want it to go. This is the way I want it to go. Get you optimum light there. When I draw a current, here you see the magnetite, we call it a compass nowadays, and it's lined up in the direction of the magnetic fields of the Earth. We're going to run 300 amperes through here, and it will change the direction. It will change the direction, which is, there's going to be a magnetic field around the wire like this, so it will go like this. The current that I run is so high that things begin to smell and smoke within seconds. The battery is not going to like it when I draw such a high current. I can therefore do it only for a few seconds. So this compass will swing in this direction and it starts to oscillate. I can't keep the current so long that it stops the oscillation. So I will stop it by hand and convince you that that's really the equilibrium position. So if you're ready for that, so we got now connection.